Okay, this question is from topic 2. Cars I and B are on a straight racetrack. I is moving at a constant speed of 45 meters per second and B is initially at rest. You need to show that the time taken for B to pass I is approximately 28 seconds if B has an acceleration of 3.2 meters per second. So you have two different Suvat equations going on here. You have a Suvat for I, car I, and you have a Suvat for B, car B. I is relatively easy because there's no acceleration. So speed equals distance divided by time. You have the speed. 45 meters per second equals distance divided by time, which you don't have either of. For car B, you have U equals 0. You don't have the time yet, but that's what we're trying to prove. You don't have the distance yet. But you do have the acceleration, which is 3.2. The distance here and the distance here must be the same because when they pass each other, they've each moved from here to here. So the distance must be the same, so we can equate that. So here we have S equals 45t, and over here we have S equals ut plus a half at squared. But u is 0, so S equals a half at squared. If we merge those together, then we get 45t equals a half at squared. And solving that for t, we get 9t divided by a equals t. And it gives you a t of 28.125 seconds, which is basically 28 seconds, which is what you're trying to prove. Part 2, calculate the distance travelled by B in this time. Now you've just equated two equations for distance, so you can use either of them and just put in the time there. So we're talking about car B, so we might as well use the car B equation. So S equals a half times A times T squared, which gives you a half times 3.2 times about 28 squared, which gives you about 1,300 meters to two significant figures. Part B, B slows down while I remains at constant speed. The driver in each car is wearing a seatbelt. Using Newton's laws of motion, explain the difference in the tension in the seatbelts. Well, we've got to here use Newton's laws of motion, so we need to mention the laws of motion. The difference in the tension of the seatbelts of the two cars, well, if the driver in B is decelerating, then that requires a resultant force. Which equals ma. That's Newton's second law. The seatbelt needs to provide that force. The reaction force on the seatbelt the reaction force on the seatbelt is the reaction force on the seatbelt. The reaction force from the seatbelt is the tension. Every force has an equal and opposite reaction, which is Newton's third law. And so in car I, there is less tension because there's no acceleration. A third car with mass 930 kilos joins the race. There's a collision. Okay, whenever there's a collision, it's usually a conservation of momentum question. So in this case, we've got two things moving at the beginning, mi, vi, plus the mass of O, v of O, equals the mass of them combined after they've stuck together, mi plus mo, times the final velocity, v2. We are trying to calculate the speed of O immediately before the collision, which is v0, or VO here, sorry. And so we can just put some numbers in there, which gives us 850 times 45 plus 930 V0 equals 930 plus 850 times 52, which gives us a VO of 58.4. We've only got stuff to two significant figures here, so 58 meters per second. The duration of the collision is 0.45 seconds. What's the average force? Well, we know that the change of momentum is the force times the time. The change of momentum of O is the initial momentum minus the final momentum. O is changing speed from 58 to 52 meters per second. So that's the mass of O times 58 minus 52 equals Ft. So the mass of O is 930, so 930 times 6 divided by T, which is 0.45, gives us F, which is 12400 newtons. Or if you've used 58.4 here instead of 58 here, then that will give you 13,200 newtons. Both of those are accepted answers.